Right, in today's stream, we're going to be looking at gravity and weight. We've got a nice, straightforward few questions to start off with, and they'll get a little bit more tricky as we go along. So first question, here we go. The diagram shows the object mass m kilograms suspended by a light, inextensible string. The magnitude of the tension in the string is T newtons. Find the direction and magnitude of acceleration. Use G is equal to 9.8 meters per second squared in all these questions. I'm going to give you 60 seconds to have a go at this. Just give you a few more seconds to finish off. My class are just finishing themselves off. Right, let's go through this question. So we have the tension going up. We have mg acting down. So the resultant force, ma, will equal, depending whether we're going up or down, T minus mg if we're going up. Okay, and if it's going down, it will come out to be negative when we do all the work. So let's put this in. So put 3 equals that in. And we've got T, what else? We've got T is 32. Minus 3 times 9.8. Put that into our calculator and we get, I've left my calculator behind. Here we go. 3 times 9.8 gives me 29.4. That's going to give me 2.6 here. So A will equal 2.6 over 3. I'll calculate again. 2.6 divided by 3. And we get 0.87 meters per second squared. And it's going to be going upward because it became out as positive. Right, have a go at question 2. Another 60 seconds. See if you can do it in the time. I'm going to stick to the time strictly this time. Okay, so draw the same diagram again. We've got T going up, we've got mg going down, and we're going to do exactly the same equation. The resultant force, which is ma, is equal to T minus mg. So we've got 0.6a equals 4.5 minus 0.6 times 9.8. And 0.6a therefore will equal, times that all out, and we get minus 1.38. And divide that by 0.6, we will get minus 2.3. 2.3 meters per second squared. So A, we equal to 2, the magnitude of A, because it does ask for the magnitude of A, would be 2.3 meters per second squared, and it's going to be downward. It is decelerating. The question is, how do I know it's not decelerating? It is well, all we know is acceleration is downwards, okay, from this question, because the A came out to be minus, so therefore acceleration is down. So it's accelerating this way. Now, if it happened to be moving up, then it'd be deaccelerating. If it happened to be moving down, then it's going to be getting faster. Okay. Right. Going on to the next question. Let's just do question 3, and then we'll move on to something a bit more interesting. So same sort of question, but we've got different unknown this time. It's A and it's not T. So 60 seconds should be enough to do this as well. Okay, so again, it's the same diagram. We've got T going upwards, we've got mg going downwards. You should always start every single question with a diagram to get a good appreciation of what's going on and to make sure you don't make any mistakes. So the resultant force, and start off with resultant force. And it tells us we're going downwards. So what I'm going to do to keep all the values positive, I'm going to put mg minus T is equal to ma. Because if it's going downwards, then mg must be bigger than T. So I'm going to put this the other way around just to keep the values the way I quite like to be. So we don't know, we do know m, we do know a, and we get 12. Actually, it didn't actually work turning it around. If I turned it around, it'd be no, the other way around, it'd be okay. Times 9.8 minus T. So T will equal 12 times 9.8 minus 12 times 6. And when you've done all of that, it should come out to be 110.4 newtons. All right, moving on. I'm going to miss out. These are all pretty much the same question, just with things changed around like that one. So we'll move on and just try something a little bit different. So we'll go to question 7 now. And this is going to take a little bit longer, so I'll give you 2 minutes to have a go at this. start going. Right, we'll start going through this. So we've got to make sure we've got our diagram drawn correctly. So we've got tension in the cable is 12 newtons. We have our ball. We have its mass times its acceleration due to gravity. So we know that 12 equals mg. So we know mass times 9.8 will equal t, because it's going to be in equilibrium. The ball is at rest, and if the ball is at rest, we're in equilibrium. So these two forces must equal each other. So the forces going up must equal the forces going down, because there's going to be no resultant force. So therefore m will equal 12 over 9.8, and m comes out to be 1.22 kg. Now we're going to replace this with a diagram where we have 15 newtons as our tension, and we've still got the same mg acting down, so therefore it's going to accelerate upwards because we've increased the force here, so it's no longer in equilibrium. So we've got MA, our resultant force, will equal everything the same direction, 15, minus everything in the opposite direction, mg. So we got 1.22, and there's going to be more decimal places kept in the calculator for this, equals 15 minus 1.22. Again, use the full decimal display on your calculator, times by g. When we work that out, we get A is equal to 2.45 meters per second squared. Essentially, the answer doesn't really matter, just that you get the equation set up right and you calculate it. Right, moving on, we're going to have a look at this question, question 9. I'm just going to try give more space and probably zoom in a little bit on that. I'm going to give you just 3 minutes to have a look at this. You can do it in less, but you're probably going to have to think about it a little bit more. I'm just going to give you an extra 30 seconds to finish off because my class, none of them got an answer yet. Okay, so let's look at this question. So the first thing we've got to do is find the acceleration because we're told that it's deaccelerating from 3.2 meters per second. So it's being lowered. So initial speed is going to be 3.2 meters per second will give us our u. And our v will equal 0 because it's going to go to rest in time equals 4.5 seconds. So if you're using v equals u plus at, that means a will equal v minus u over t, which will be minus 3.2 over 4.5, which gives us an acceleration of minus 0.7111 and so on meters per second squared. Now, the velocity was positive that way, our acceleration is negative, so that means accelerating this way. And it's quite key to spot that the acceleration is going upwards here. So on this diagram, we've got the thrust going up and we've got the weight of the platform acting down if we resolve on the platform. So if we resolve vertically, we're going to have MA, as this is negative in this direction, it's going to be positive in that direction. So we're going to have MA will equal the T minus the mg. So remember, because the velocity was down was positive, the A became negative, which means it's going up. So if I want MA is going up and being positive, then T minus mg will give me my resultant force, MA. And so therefore we've got 120 times by 0.71 recurring equals T, the thrust, minus mg, 120 times 9.8. So T will equal 120 times 0.71 recurring plus, that's going to be a plus, let's just change that so it looks like a plus, plus 120 times 9.8. And that comes out to be 1,261 Newton to the nearest Newton. The key element of that one, if you were struggling with it, was to make sure you got your work out which direction the acceleration is going in, because it's actually slowing down as it comes down. That means acceleration must be actually acting upwards, which seems to confuse a few people. Right, moving on, we're going to look at some equilibrium questions. So let's just get the view out a bit so you can see both. Okay, hopefully you can see both of these. Which of these two are in equilibrium? Give you 2 minutes to think about that. The whole class has finished that already. If you just want to be, if we're going to be very thorough and we resolve this one vertically, we can see that the resultant will equal 13 plus 6 minus 20. And you see that comes out as minus 1 Newton acting downwards. So therefore, this is not in equilibrium. We don't really need to go any further. Equilibrium. Sorry about my spelling. Okay, and the next, so maybe it might be the next one. So if we've got 12 acting upwards, we've got 12 acting downwards, so they're equal. We've got 8 acting to the right and 8 acting to the left. So yes, this one is in equilibrium. Okay, work out if this one is in equilibrium or not, and you have 30 seconds to do it. Time's up. So we're going to have the resultant, if there is one, will equal minus 4, 9, plus 4, 3, plus 0, 12. Minus 4 plus 4 is 0, 9 plus 3, and I've just made a mistake because that's a minus 12 in there because it's acting down. Gives me 0 as well. Therefore, it is in equilibrium as well. Right, I'm going to miss out that question. We'll just zoom in a bit. Maybe not that much. And we'll do question 5 here. 2 people are trying to move a heavy box lying on the rest on the carpet using 2 light inextensible ropes. The tensions in the ropes are such. Here and here. I and J point east and north respectively. The box remains at rest. Find the magnitude of the frictional force. I think you can do this in 60, but I'll give you 2. Okay, that's your 2 minutes up. So 2 people trying to move a heavy box lying at rest on a carpet using 2 light inextensible ropes. The tension of the ropes are 32, so our resultant force from the tensions will equal 32, 12 plus 25 minus 18. So we add those 2 together and we get 57. And we get minus 6. So that's our resultant force for the 2 ropes. So therefore, the friction will equal minus 57 and Sorry, did I say 6 and I've written 8, haven't I? Yep, that should be a 6 there. 57 and 6 should be in the opposite direction. But that's not what the question asks for. It actually asks for the magnitude. So the magnitude will equal the square root of 57 squared plus 6 squared square rooted. And that, I think, comes out to be about 57.3 Newton. Okay, I've got to ask why I've changed this from 57 to minus 57. This is the resultant of the two tensions. So if we have the two tensions, so we've got 32, 12 is that direction roughly, and 25, 18 is that direction. If we were to replace them with one force, then it would be a force that would be 57 minus 6, so that would be that direction. So that would be our resultant force that we would replace them with. And if it's lying at rest, then friction must be in the opposite direction. Yeah, it must be equal and opposite to that resultant. So the actual friction would be minus 57.6 newtons, and then you can find the resultant by squaring these nutties together. Any questions? Resultant minus friction equals 0. Well, that's our resultant. Take away that, you'll get 0. Yeah. If you took, well, no, sorry, no, you add the friction to the resultant. Sorry, you add the friction to the resultant to get 0. You've got the frictional force could be added to the resultant force to get 0. It's got to be opposite to the resultant, because the resultant must be the combination of these two tensions. Okay. The resultant, there's your first tension, there's your second tension. These are your two tensions. We replace them with one resultant. Therefore, that is your resultant force. Now, if that is not negated, then the thing will start to accelerate. And as it's not moving, okay, because the box remains at rest, the friction must be in exactly the opposite direction. Right. Okay. We'll finish off today with this question. The sheets will get harder as we go through them, but it's important to get the concepts right with straightforward questions. Even that last question had some interesting questions from the class as in terms of the direction of the friction. So anyway, give you 3 minutes to have a go at this question, and then we'll finish off there. acting in opposition to these two. So actually, f must equal, if we were to put it in vector form, we know that these two are going to be minus 17 and plus 25 in the x and the y direction. So f must be 17 and minus 25 in vector form. So the horizontal and vertical components, the horizontal component is 17 and the vertical component will be minus 25. Otherwise, this will start to move. If it does not oppose these two forces, it will start to move. So the magnitude of f, these two lines mean magnitude, and that's going to be equal to 25 squared plus 17 squared square rooted. And when you've done all of that, I think it comes out to be 30.23 newtons. Now we want to find the angle it makes to the horizontal, so we're going to go 17 along and 25 down. And we can find that angle there, which will be tan theta will equal 17 over 25. Therefore, theta will be inverse tan of that, which comes out to be 55.8 degrees below the horizontal. Okay, so we'll be back here again 4:30 tomorrow, and we'll be looking normal reaction forces questions, and we might get on to some connected particle problems, although that's probably a lesson, all of it. All the other lessons after that are lessons of their own. Okay, so we've got in the series at least 1, 2, 3, 4, 5, 6 lessons in this series to go to complete the idea